Dear guests, hi. Thank you for joining us. We start in a few minutes.
Okay, colleagues, I think we'll start now. Um, my name is Viktor Dobnikov, and I'm co-founder at EECVC. And today I'm going to moderate day 2 of our online EECVC 2020. Yeah, first of all, I'd like to welcome all of you here. Hope more to join. I'd like to remind you also that we have day 3 dedicated to business and investors. And there will be father of our conference, Vitaly Goncharuk. Perhaps he is preparing double after party for next year due to the fact that we missed it this year, unfortunately. But today we're going to make second day a bit more interactive than the first one was. And we will try to do it with rooms in Zoom. So we will share in chat room names dedicated to several topics in machine learning and computer vision. and please put the number of room at your name, just your name you're in list, and put the number of room you want to chat. There will be 2 rooms dedicated to today's talks and today's speakers, and 4 more rooms. And you will go to these rooms when in break between talks, and have 15 minutes to talk within some topics or with today's speakers. And also I'd like to remind that all the questions raised during the talk you may put into the chat, and after the talk there will be a dedicated time slot to answer those questions. And also it's up to speaker whether he wants or not to answer some questions interactively. So I think with this, that's it for organizational part. We will repeat this in chat again, so about room names and their numbers. And now I want to introduce your first speaker, Andrian. And Andrian actually is a researcher, research scientist at Samsung AI Cambridge, and his research interests lie in the intersection of computer vision and machine learning. So pretty relevant to absolutely relevant to conference and topics we cover. And I'd like to pass word to Andrian. Yep.
Hi, Victor. Hi, everyone. Thanks for introduction. Okay, let me share the screen. Okay, I assume everyone is seeing the screen.
Oh, yeah, perhaps yes.
Okay, great. Okay, so hello, everyone. It's a great pleasure to be here, even if only virtually this time around, especially that I keep hearing so many great things about the after party that was supposed to happen. Now, a few words about me. I'm Andrian. Previously, I did my PhD at the University of Nottingham in UK as part of the computer vision laboratory. My work there spanned and continues to span on various subtopics of human analysis, be it key point estimation, 3D reconstruction, or super resolution, and simultaneously on efficient models, mostly via extreme quantization. Currently, I'm based in Cambridge at the Samsung AI Research Center. The goal of today's presentation is to offer our introductory view to quantized and later on binarized models, explaining in the process what is quantization and what are its benefits. Furthermore, we'll go through the common challenges and methodologies for successfully training quantized and binarized models, presenting a few of our recent works that further advance state-of-the-art for binary networks. Structure-wise, as mentioned earlier, we'll start by defining what quantization is and what are its key advantages and limitations. We'll mostly focus initially on 8-bit quantization techniques, but please bear in mind that most of these things can be applied with various degrees of success to lower bit quantization. We simply select 8-bit as the main object of study due to its mainstream support in terms of both hardware and software. In the second part, we will extrapolate what we learned on 8-bit quantization section to the most extreme case of quantization, also called binarization, where I'll present also some of our recent work there. Finally, we will discuss about our very recent approach that combines binary networks with neural architecture search. By the end of this presentation, I hope that you'll either have a strong starting point if you are interested in either adopting low-bit quantization to your pipelines, or why not adventuring into improving their performance further. With this, let's get properly started. As many of you know, current state-of-the-art deep learning-based approaches can achieve results of remarkable accuracy on a wide variety of tasks, exceeding in some cases the capacity of an average human expert. This expression became an ubiquitous component of many research papers and clearly showcases the maturity reached by deep learning-based approaches. Though what made this a successful recipe? Why does deep learning thrive in general? Firstly, the internet has allowed various entities to collect huge amount of data with correspondingly large-scale labeled datasets being annotated, such as ImageNet, Microsoft Cocoa, Kinetics, and so on. Then there are quite a few methodological improvements, such as the adoption of reuse activation functions, the addition of batch normalization, residual connections, alongside, of course, better initialization strategies and network topologies, all together have significantly advanced the state of the art in the recent years. Now, none of this will have been possible without the dramatic increase in the computational power that happened basically at the same time, closely following Moore's law. A typical example that you'll hear nowadays is that an average smartphone has more computational power than NASA had when they first launched a man on the moon. Now, on the last point, while the first two are largely independent of the device on which they are deployed, the last aspect, the availability of computational resources, is often the most limiting factor. To elevate this, a large variety of meta methods and directions were proposed, such as weight pruning, where one tries to remove redundant, less important weights, weight specifications and filter decompositions, designing efficient architectures obtained either manually or by deploying various automatic network search strategies, and finally, quantization. Note that many of these research directions are orthogonal with each other and can be potentially combined with various degrees of success. While here we'll mostly investigate quantization, it's still important, I believe, to have a broader view in mind when looking at it. Before talking about it, let's have a brief look on how numbers are typically stored on a machine. The slides mostly focuses on data stored up to 32 bits or less, since it's pretty uncommon to use for deep learning more than 32-bit precision calculus nowadays. As you all know, we can either represent the numbers using fixed point representation or floating point. The floating point representation is generally more advantageous since it allows for a significant wider range of numbers to be represented, as we can see in the column from the right. Now, the structure typically reserves 1 bit for the sign, and depending on the type of representation, the rest can be divided between the mantis, also called the fractional part, and the exponent. Relatively recently, the community realized that networks can be in fact trained with lower precision than the traditionally used FLOT32. As such, FLOT16 was popularized and gained in hardware and software support. Despite the significant drop in number of unique values that can be represented, training such networks is generally stable. Finally, in the most extreme case, we can keep only the sign bit itself. Given this, we consider as quantization the conversion operation that decreases the number of bits used to represent the operands. This allows us to perform arithmetic operations using fewer bits. But now, what is with all of this desire for having less accurate computations? Aren't they harmful in practice? Well, yes, but at the same time, the more bits you have, the more complex and power hungry your circuits is going to be. For example, on a 45 nanometer process node, a typical gate, as reported by Horowitz et al., is 3.7 picojoules per multiplication on a FLOT32, but this number decreases by 3 times when these computations are performed on FLOT16. The gains are even more dramatic once we drop to 8 bits. Finally, in the extreme case where we have a single bit, the energy consumption drops by a few orders of magnitude. It's not only though about multiplications. Reading data from the memory and moving it around incurs a significant cost in energy. As such, fewer bits can also reduce the memory bandwidth required. With this in mind, let's focus on why would you want to use overall the quantization. Focusing again on the most adopted cases, that of INT8. Firstly, we can reduce the model size and memory bandwidth by 4 times. Depending on the implementation of operations used and the hardware running it, we can expect 2 to 4 times faster models when compared against FLOT32. In addition to this, INT8 reached a good maturity level. All major CPU and GPU vendors have some form of native hardware support, while pretty much all deep learning models can be quantized successfully to these degrees. For example, both TensorFlow and PyTorch supports directly exporting models to Android devices. And unless you have some really unusual scenario, you don't have to redesign your model architecture. So you can use the same previously designed and tweaked model that you had. So we talked a lot of it, about it until now, but how do you perform it? So firstly, we need to find a way of dropping the number of bits without decreasing as much as possible the representational power of the model in terms of output prediction. So let's imagine that we have a bunch of features or filters, if it's for the weights, with values between a minimum and a maximum value. All these values between them are represented using single precision in our case. We'll want to define such a mapping that transforms all values from this range to one of a 2 to the power of n minus 1 state, where n in our case is the number of bits. The simplest type of quantization that we can probably define, and the most intuitive one, is to simply do an uniform affine quantization. And as its name implies, giving a computed scale factor, which we'll talk about later, we define a set of n equal intervals. In addition to this, we also define a 0-point bias that ensures that zeros is mapped without any errors. This part is quite important because we want, for example, operations such as padding to not introduce any additional noise. Now, as you can notice, the presence of this additive 0 point can cause some issues with the efficient implementations. And as such, a simplified form can be considered, which we'll see in a moment. Note that in the case of a convolutional layer or a linear layer for that matter, we can compute the scale with different granularity levels, either one scale per channel, or more simplistically, we can compute a single scale for all the channels inside our layer or activation features. So as we mentioned earlier, we can simplify the affine quantizer simply by setting the 0 point to 0, creating an asymmetric uniform quantizers. While this is simpler to implement and faster, it does tend to result in weaker models. We'll talk more about how they fare in terms of accuracy later on. Another variant of this was proposed is the proposed stochastic variations shown here. Basically, we had some additive noise drawn from a uniform distribution to the to be quantized values. This was believed to produce better models. The recent results point that there are no actual real benefits in doing so in general. Plus, the hardware support for such form of quantizations is quite limited. While uniform quantization techniques are hardware friendly, empirical study has shown that typically the weights follow a long tail distribution instead of a uniform one. So some of the values, if we simply assign the same number of possible states for all ranges, some of them will be underrepresented while some of the other due to the data distribution. So as we can see here, a big portion of the weights are concentrated around the mean, and only a few outside of it often called outliers. Similar distributions are also present for the activations. So one now will expect to assign higher number of intervals, so higher resolution around the mean. However, uniform quantizers fail to do this. At the same time, attempting to address this using a non-uniform quantizers incurs significant computational costs. So we need to find a way of doing this efficiently while addressing this at the same time. To elevate this, powers-of-two quantizations levels are then proposed. Because on one side, they allow for cheaper multiplication since we can implement them using bit shift operations directly on hardware, while simultaneously they increase the resolution around the mean, as we can see in our figure. Notice that from it, most of the levels around most of the steps are located around the mean. So did we solve the problem with this? Well, let's see what happens, for example, if we increase the number of bits from B to B plus 1. In this case, due to how this distribution is drawn, the new level introduced due to the increased representational powers will be introduced again in the region proximal to the mean. So again, as we increase the number of bits, the resolution keeps increasing around the mean. However, there are no significant differences for the rest of it. So the regions, that regions become more underrepresented, and we are using more bits without having a significant gain in accuracy. A recent proposed solution at ICR 2020 is the additive power-of-two quantizations that defines the intervals by taking a sum of k-bit width terms, also called the base width. And as the figures show, the newly proposed scheme increases the number of quantized levels, both in the region close to the mean, but also outside it, making better use of the entire interval as the number of bits increases. Here we can see how the intervals are defined for the case of unsigned numbers, but the same can be applied to signed ones. In the equation, gamma is a scaling coefficient that makes sure that the number stays in the alpha range. More concretely, let's have a look at a simple example. So for b equals 4 and k equals 2, we can define the following sum of terms. Note that the states will be obtained by taking all possible combinations between P0 and P1. So in total, we'll obtain, in this case, 16 states. While there are other variations of these methods, these are the most common ones for quantizing it. And in principle, any of them for typical networks will suffice, but depending on how exoteric your architecture may be, you may have to pick one or another. Now, unlike linear or convolutional layers, the batch normalization layers are typically more sensitive to quantizations. Partially, which is due to their differentiated behavior that happens during training versus during the test phase. During training, the mean and the variance are computed based on the current batch, while during testing, they are frozen, and we are using the accumulated moving average of the previous batches saw during training. The first aspect allows us to safely fold them into the convolutional weights, improving both the speed and stability. However, it's unclear how exactly to perform the training procedure in this case. On one side, keeping them fixed during the training we will never compute or update them, and this will lead to poor results and performance. At the same time, if we dynamically change the values, this will lead to instability during training, especially early on, since the values will change quite dramatically. As a common ground for the two, correction scaling factor C was proposed that ensures the stability during training with respect to the changes in the batch mean and variance that is computed as variation between the statistics of the current batch and the global ones. Early on the training, however, in order to preserve the behavior of the original batch norm, the effect of the correction factor is undone every time after the convolutional output is produced, as we can see. However, once we advance during training, this is stopped from happening. We are freezing the statistics, and we're fine-tuning for a few more epochs using the accumulated statistics. As such, minimizing the discrepancy that we have between training and testing, since this phenomenon is especially more important for quantized networks. Now that we hopefully have a good idea on how we can quantize individual types of layers and what kind of functions we can use for this, how can we actually do this? Let's see how we can actually do this in practice. More generally, we have two approaches. The offline one, where we can take a pre-trained model and without retraining it, we can create a quantized version of it, or the online version where we fine-tune or retrain a given network from scratch. While the first one is, of course, much faster to do and does not require retraining, the second one tends to generate more accurate models. The offline case, actually in both cases, the most important component perhaps is computing the scale accurately. For example, for offline quantization, we have two distinct cases, one for the weights and the other one for the input features. For the weights, we can simply compute the minimum and the maximum that we saw earlier in the figures to determine the quantization parameters based on them. For activations, we can simply compute the moving average of the minimum and the maximum. There are more fancy approaches that we can do here, such as computing the KL divergence between the distributions of activations. for the pre-trained float42 model and the to-be quantized int 8.1. While they tend to work better, for most practical cases, the difference will be relatively small, and this will be significantly faster and easier to implement. A much stronger one, but also a bit more laborious perhaps, is the online quantization, but basically involves training a quantizer and a quantized network from scratch, or from fine-tuning one from a float42 model. As such, during training, we perform a so-called fake quantization. And while these layers work still at full precision, we will artificially reduce the number of states as they will be quantized. In practice, it just means that we apply the above-mentioned quantization functions to the weights and the features of the model at train time. So during the forward pass, we obtain the quantized states. However, during the backward, we update using real-valued gradients the real-valued copy of the quantized values. You will also perhaps notice that none of the functions used for quantizations have good gradients. A popular solution to overcome this is to simply provide smooth gradients by computing the derivative using a straight through estimator. So just like a clip functions, for example, like a clip identity function, for example. So which one is better out of them? As this figure shows, and while this figure does not include the quantization done on an online fashion, it's good to notice that there's practically no difference between a float42 model and an int8 version. From the offline quantization techniques, also called post-training quantization, we can see that the one that preserves that fares the best and preserves the accuracy better is the asymmetrical per channel one, where we compute an independent scaling factor for each channel. Here we can also see from the figure that bigger models with more weights are typically easier to quantize, which is perhaps unsurprisingly because we already start from a much larger capacity. So to conclude on this part, until this point, we saw that int8 quantization models can be up to 4 times smaller and faster. Bigger models are easier to quantize. Channel-specific scaling factors are kind of always better. And fine-tuning from a pre-trained or single precision model is typically preferred since we can get a faster convergence. Finally, batch normalization layers require a more specific and special treatment due to their dual behavior during training and testing phase. In fact, for added stability, typically what the community does is, depending on the ordering of the layers, we take the convolutional batch norms and ReLU and we fuse it in one single operation. Our journey into low-bit quantization doesn't stop here, however, and even following, we'll move towards studying the most extreme case of quantizations, also named binarization, where we'll be using some of this single bit, we'll be using one single bit to store the operands. So can we actually go all the way down to a single bit? Sometimes. However, training such networks is complicated and remains an open problem, with current works attempting to reduce the large accuracy gap between a real-valued network and its binarized counterpart. Most of the difficulty arises from the discrete nature of binarization, with gradients being uninformative that can either fade or explode. There is also high sensitivity to distortions, since small changes can make the jump between the two states. Given that binarization is intuitively difficult, why do we care? Well, beyond the energy savings that we saw in the beginning, binary convolutions are up to 64 times faster and 32 times smaller on a modern x64 CPU. Such networks typically outperforms in terms of efficiency by far any other types of network compression or quantizations. Not only they are faster, but they can also lead to lower battery life and to higher battery life, smaller application packages and updates. I'd also like to point out that this is the absolute fastest quantization that can be achieved, since 2, as we all know, is the minimum number of states that still allow for the information to be represented. These gains that we see here in terms of compressions and speedups at least on a CPU, are simply coming from taking advantage of a SAMD concept. In particular, we can pack 32 of 1-bit parameters into a float and then replace the multiplication with bitwise XNOR, followed by a pop count that counts the number of bits of 1. So what exactly is a binary network and how does it work? Well, giving a real valued convolution of input I parameterized by set of weights W, its binary counterpart is defined by simply taking the sign of the input and weight tensors. Furthermore, typically the binary weights are scaled using a real valued scalar factor. Note that in a binary convolution, both the input features and the weights are binary, which allows us, as we were mentioning earlier, to replace all multiplications with bitwise operations. While there is more to teach on how to make this actually trainable, for brevity we'll omit for now these details. We also tend to typically change the orders of layers. So while typically you have a post-activation style of ordering where you have a convolutional layers followed by a batch norms and your activation function of choice. For the binary ones, we typically put the binary the batch norm layer first, followed by the sign, convolution, and finally, if another activation is desired, it can be added afterwards. The reason for this is that the batch norm layers scales and centers our distribution firstly around 0, and at the same time it behaves as a dynamic quantization point, where depending on how the batch norms is going to split the values using its bias, the quantization point is going to be shifted, in either directions. We can probably understand by now again that the key component that leads to high-performing binary networks is again that scaling factor. As proposed by Rastegara et al. In the landmark XNORNet paper, the weight scaling factor is computed analytically as the mean of the absolute weight values. In addition to this, the XNORNet methods also calculated a second scaling factor for the inputs. However, the latter had to be recomputed every iteration, and as such it was relatively expensive and offered very modest performance gains. A better approach is to compute it discriminatively, learning it via backpropagations. Instead of learning the alpha in such a way as to minimize the reconstruction loss as done in XNORNet, we simply train it via backprop to minimize this with respect to our target loss. While typically it is computed by learning a scaling factor for each set of 3D weights, recent methods also tested going further. So to elevate this, and to improve the capacity of a scaling factor, another trick that we can do is instead of learning one single scaling factor per each channel, we can take advantage of a representation of the weights and learn one scaling factor per each dimensions. So one for the channels, another one for the width of the kernel, and another one for the height of the kernel. It is quite similar in practice with learning a rank 1 CP representation of it. Now, when all of this are learned during training and during the forward time, they can all be combined in a single one. So we will avoid any increase in computational powers. For example, by simply switching from the analytical form to the trainable one, we can gain more than 4% on ImageNet in top 1 accuracy, and by adding the second 2 ones, we can gain 1% more. We saw previously for the case of quantization that the derivative of the quantizer is typically approximated using a straight-through estimator. A similar approach needs to be taken here. As we can see, the derivative of the sign is an informative and is just a spike around 0. The most popular and computational cheap approach is to use the derivative of the hard tangent or the clip function, which is 1 in the range -1, 1, and 0 everywhere else. Of course, multiple alternatives were tried with various degrees of success beyond this. A few noteworthy ones are using the tanh as a soft approximation, soft sign, or various types of polynomials. Some more recent approaches attempt to define this in a dynamic manner based on the data itself. Since this difference in gradients poses major since this difference between the computed gradients and the actual gradients is quite large, this poses quite a big challenge during training. So what we tried here was to do this gradually. So starting from, let's say, a tanh function, as the training advances, we're using a parameter lambda, we control the stepness of the function. So as the training advances, the function will be more and more similar to the sine function. So for example, for alpha 1, this is the distribution of the weights that we have. And as we can see, as alpha increases, most of the weights become quantized to either -1 or 1. This allows for, on one side, for smoother transitions, and it allows the models to get significantly better gradients early on in the training. With this in mind, now let's look at the few failure cases that can occur when training a binary network. Broadly speaking, there are 3 types of failures cases that can occur based on the distribution of activations. We have a degeneration, saturation, and the gradient mismatch that we just mentioned. Firstly, first, as we can see in these figures, we refer by degeneration as a problem where most or all the values are found on one side of the sine function, be it on the left or the right. In practice, this is a pretty uncommon situation since such solution can't produce viable models. Since if all the values are either 1 or -1, we will always get the same prediction no matter our input. Saturations occur when the distribution of activation is wider and significantly goes outside of a range -1, 1. Since the values outside of this range, -1, 1, receive a 0 gradient, they get stuck and they will most likely never change their state. So they will be, once they go very far away from 1 and -1, they'll just stay at that value most likely. Finally, we have a gradient mismatch what we just talked about. Assuming that the activations follow a Gaussian with mean mu and standard deviation sigma, values that can be computed during training from the input 3D tensor, one can define a set of penalties of the distribution itself as a whole to make it well behaved, solving these degenerations problems that they may occur or elevating these via such penalties as tried by Ding et al. In a recent CVPR work. Unlike in-type quantizations, where we said that we can typically preserve models architectures, the same isn't really true for binary networks. We already saw that it's beneficial to replace the ordering of the layers, but this doesn't stop here in practice. So let's start from the basic block from our resident module. A simple variations of it that was proposed for binary networks was in the BiRealNet paper, where they added these double skip connections. So while this sounds like a very small change, this itself can improve accuracy by 2-3%. The reason for this is in the representational power that grows in this case. So at the end of a convolutional layer, let's say we have a very limited number of possible states. Now, thanks to the additional skip connections, we can basically increase significantly of the number of possible states that can be represented, especially that these ones are coming before the batch normalization layer. Finally, another variations, architecture variations, was proposed at ICCV. And as we can see, this final block depicts a structure that splits a 3x3 block into 3 components. improving at the same time three key aspects. On one side, we increase receptive field size by having kernels that work at 3 different resolutions. On the other side, we improve the gradient flow, since there is now a direct path between the final output and each of the layers that can pass. And finally, we add a prelude after each of them, which allows for both signed and unsigned informations, signed and positive, negative and positive information to pass through. Previously, we discussed that a fixed scaling factor is computed in order to retrieve part of the lost signal magnitude. The entire flow of information entering the convolutional layers is as follows. As activation enters a binary block, all are still real valued. Batch normalizations sent as activations, which are then binarized, losing a large amount of information. Binary convolutions, rescaling, and prelude follow. Here we propose to use the full precision activations signal available prior to the large information loss incurred by the binarization operations to predict the scaling factors used to rescale the output of a binary convolution channel-wise. As such, we can compute a set of data-dependent factors in a dynamic format that makes use of information present into the signal prior to binarizations. This design of the scaling computation is similar with what we see in what we saw in the squeeze and excitation paper, except that this time the input is taken before entering into the convolutional operations. We also make a reasonable assumption that if a binary network is trained so that its output matches that of a binary convolutions of real convolutions more closely, then we can define a loss to encourage this. This is also similar with the assumptions drawn into the original XNORAD paper, where the scales are computed such as the quantization's loss is minimized. However, they do not impose any explicit loss between the two networks in a knowledge distillation fashion. In order to make this training robust, we have to do this gradually, since it's kind of known that if your teacher is significantly better than a student, then you typically get less improvements on accuracy in comparison with the case where your teachers and the students will be of a more similar performance. So for this, we first train a real valued with all the weights a real teacher, and using it we guide a student with binary activations but real weights. Once this is trained, this model becomes the teacher for the next step, where we finally train a fully binary models where we binarize both the weights and the input activations. In addition to these, there are a few training tips that can be used to further improve performance. It's typically better to use ADAM and RMS-prop kind of optimizers that have a built-in scale for your gradients. Otherwise, SGD tends to cause more troubles in practice and can quite often lead to nuns. Also, while we didn't explicitly say it here until now, the distribution of the weights is typically forcefully zero-mint, though this also happens kind of naturally. So it's more of an insurance of making sure that our weights are not going to be far off from a roughly 50-50 split in terms of positive and negative values. As for the quantization case, discriminatively learned factors perform better, and if computational budget allows it, using real value downsample layers, for example in ResNet, that is for the layers located before the skip connection, can significantly improve the performance. And again, a multi-stage or a two-stage initialization process where we have first a real valid model, and then we train a model with binary inputs and real valued, and then from this we finally get our binarized model, tends to offer better performance. This is, for example, the improvements that we gained by adding both the data-dependent computation of the scaling factors and of distillation between the features of a real student and a binary one. So these two alone can improve on top of the previous methods by more than 7% on ImageNet. Further one, we'll talk on combining binary networks and network architecture search in the same idea that we discussed previously, that for binary networks, we typically need different kind of architectures. So here, for the first time, we'll explore the problem of binary architecture search. And we show that directly, the fact that directly applying NAS to the binary domain provides very poor results. To elevate this, we describe to our knowledge for the first time, the 3 key ingredients for successfully applying NAS to the binary domain. Specifically, we introduce and design a novel binary-oriented search space. We propose a new mechanism for controlling and stabilizing the resulting search topologies. And we finally propose and validate a series of new search strategies for binary networks that lead to faster convergence and lower search times. One of the key components that makes NAS successful is their constrained search space. Its quality being often the determining factor on how good the search architecture can perform. Since searching across a large space is computationally prohibitive, most often the recent NAS methods manually define a series of 8 operations known to produce satisfactory results when used in handcrafted networks topologies, such as 3x3 and 5x5 dilated convolutions, separable convolutions, and so on. We note that for real valued networks, random search performs on the aforementioned CIFAR10 achieves 3.29 top error versus 2.76 when used to search an architecture using darts. However, not all operations used for the real valid case are suitable for searching binary architectures. In fact, we found that when using the standard dart search space, searching in the binary domain does not typically converge. It is due to several reasons. The depth-wise convolutions are notorious hard to binarize due to what we call the double approximation problem. The real-valued depth-wise convolution is a compressed approximation version of a normal convolution, and in turn, the depth-wise is a quantized approximation of a real-valued one. Furthermore, the one-by-one convolution layers and the bottleneck blocks were already shown to be harder to binarize because the features compression that happens in such models amplifies high information degradation already caused by binarization. With this in mind, we propose a new search space constructed from a binary first point of view that avoids or elevates the aforementioned shortcomings. While we preserve the zeros and identity connections alongside the max pooling and average pooling layers, which do not contain learnable parameters anyway, we propose to replace all the convolution operations with grouped and dilated group convolutions. This removes all the one convolution layers, gets rid of the issue of having separable convolutions, while maintaining the efficiency via the usage of groups. Now we know that due to gradient mismatch, exploding or vanishing gradients are more likely to occur for the case of binary networks. And to improve this, in all convolutional layers, the depth of all operations used is set to 1, meaning that we used 1 convolutional operator per layer, as opposed to up to 4 in the case of a dart search space. Another consequence of using operations with a depth equals to 1 is that we can improve slightly the latency of our architectures due to effectively shallower networks. Finally, in order to improve the gradient and information flow, which is even more critical for the case of binary networks, while also speeding up the convergence of such operations during the network search phase, we explicitly add an identity connections on all convolutional operations. Now, despite its accuracy and appealing formulation, dart's accuracy can vary widely between runs depending on the random seed. Often it can collapse to degenerate solutions that contain mostly skip connections. While there are various heuristics proposed to elevate this for real-valued networks, we find that most are suboptimal for binary networks. Furthermore, given that during search, the input to the node is obtained by taking the weighted sum, the network tends to cheat, and it creates a nearly uniform distributions on all the operations. To elevate this, and to encourage the network to make harder, more discriminative predictions, we propose to use a temperature factor basically a Gumbel softmax with a temperature lower than 1. This has the desirable effect of making the distribution of architecture parameters less uniform and more spiky. Hence, during training, because the information streams are aggregated using a weighted sum, the network cannot equally or unequally rely on all possible operations anymore. Instead, in order to ensure convergence to a satisfactory solution, now it has to assign the highest probability to a non-zero path enforced by a subunitary temperature. This behavior also follows closer the evaluation procedure, where a single operation will be selected at the end, reducing as such the performance discrepancy between the search, where the network pulls information from all paths, and the evaluations. As we can see in the figures from the slide, as the temperature decreases, the number of convolutional operations selected increases significantly, while that of skip connections, zero ops, are diminishing. We note that architectures in which the skip connections where max poolings are overly selected are typically degenerate solutions that do not lead to successful or useful networks. Now, since binary networks are harder to train, we propose to perform the search only binarizing the activations. As such, our results show that this correlates well with the final performance of a full binary network while being faster and easier to train. Overall, our approach is capable of discovering high-performing binary cells, offering new or validating existing insights about what an optimal binary topology should be. As depicted, the cells found tend to prefer convolutional layers with larger kernel sizes, such as 5 by 5, which helps alleviating the limited representational power found in such networks. In addition to preserving information flow, a real valued path that connects one of the input nodes to the output is always present. Furthermore, since the downsampling operation compresses the information across the spatial dimension, to compensate for this, the reduction cells used in places where the resolution changes is typically wider, so more information can flow at a given time, as opposed to the normal SER, which generally has a more deeper distribution. Here is a comparison with some real valued cells found, for example, by PDART. As the results show, our method significantly can outperform the current SOTA-NAS methods, typically deployed for real valued networks. A similar trend can be noticed on ImageNet, where we outperform previous methods by more than 6%. And again, on CFAR against general methods, our method outperforms previous ones by more than 4%. In conclusions, we've shown that the proposed methods can further bridge the accuracy gap between real valued and binary networks. And at the same time, a carefully designed NAS can equally result in better and more efficient binary architectures. Carefully designed losses and scaling factors alongside the attention mechanisms can also significantly improve the accuracy of binary models. Finally, binary models can offer huge speedups and compression rates, especially on custom hardware such as FPGAs, where we can implement them with a significant smaller area of circuits. With this, my talk concludes. Thank you for your time, and if you have any questions, feel free to ask.
Thank you, Adrian. We do not have questions in chat, so colleagues, you have please just unmute and ask your questions here.
Hi. I have kind of research question, like not directly related, but so do you know this lottery ticket hypothesis series of work?
Yeah.
I think in one of the later the so-called like super masks, which basically is like binarized version of the trained network, which performs almost as good as, well, okay, not binarized, but like masked, you have zero or floating weights as Is it somehow connected to like methods to binarization you mentioned, or it's like different? With this, I don't understand.
I guess you could potentially combine it, but I don't think they're necessarily directly connected. In general, obtaining a good network and a good set of weights can be surprisingly easy in some sense. For example, there is work that shows that you can just take a random set of weights, having a certain means and variance, and you can select out of them while keeping them fixed only the weights you want, and you'll still get a network that performs similarly with a ResNet. However, I don't think there is any work that really try to combine these for binary networks. And the typical procedure for training them is via backpropagation directly. So not by sampling or anything like this.
Thanks. One more question on practical. So how do you think, like, how is this PyTorch or TensorFlow like functions of like far from research in terms of binarization? I know that TensorFlow supports some kind of out-of-the-box 8-bit quantization and so on. So like how far are they, like 2 years before
So INT has now full support in both of them for quite some times. CUDA11 has some experimental support for binary networks. I'm not sure exactly when there will be wider adoptions from the big frameworks. I assume it's a question of when the accuracy will be sufficient to attract more industrial interest on this. But there are already quite a few frameworks from various companies that are emerging in terms of binarizations. So, for example, there is missing now the name. Yes, there is LARC, for example, that recently, a few months ago, released binarized convolutions and operators that can be used together with TensorFlow and Keras. And they show pretty much close to 64 times faster models for the convolution operations themselves.
Wow.
But again, to conclude, I'm not sure exactly when PyTorch or TensorFlow will incorporate such features directly.
Okay, thank you.
Okay, colleagues, any more questions to Andrian? Okay, there are some attendees who selected the first room, so perhaps there will be some kind of live chat there. Thank you, Adrian, for your talk.
Thank you for the invitation.
Yeah, thank you. And now Elena will distribute everyone between rooms according to selected numbers. Those who were not selected will be in general room just here. And I think we will make a 10 minutes chat instead of 15 minutes, since it's already 8. And then everyone will automatically return to main stage. And we will start, and we will continue with Daniel's talk. So meet you all here in 10 minutes and have a good talks in rooms. Hello back, colleagues. Okay, so perhaps probably some chat started and might be continued either after the conference or probably during some other slots. I'd like to remind that after the conference, there will be a kind of free chat time within the same rooms, but you may change your rooms numbers so that it will be possible to permutate attendees in different rooms. And now it's time for Daniel, for Dr. Daniel Barath from the Center of Machine Perception from Czech Technical University, Prague. And hi, Daniel.
Hey,
and, yes.
So you all hear me and see me?
Yes.
Yes, good. You interrupted the best conversation of my life, and then I have to get back to the general room.
You may continue it after.
So have a nice day, everybody, or evening, everybody. I'm happy. I was very happy that when I got to news that I can get to Ukraine, but in the end, it's not like that. But I will go next week, next year. So let me share my screen, which is. Do you see my screen?
Yes.
Yes, I'm happy. So let me start the presentation. A few words about me. I'm working at CMP like Dimitro, and also at the in Hungary, in the Hungarian Academy of Sciences. Mostly I'm working with robust estimation and some geometric stuff. And today I will be talking mostly about ransack and robust estimation things. Okay, if you have any questions, feel free to stop me. So I think it could be more like a conversation. If you have any questions, then I can easily answer. Okay, let's start the presentation. So I will be talking about ransack and such things. But first of all, let's us discuss what is model fitting. We can talk about different things when mentioning. So for example, we can talk about standard single class. Somebody is too loud. I heard some nose thing. I don't know the word in English, but so yeah, when estimating models, we can talk about different things. For example, we can talk about standard single class, single instance model fitting, which means that if we stay at this simplest example, I will mostly talk about these simple cases, the 2D line fitting, because that's the easiest to be imagined. And the standard single class, single instance case is when we have a set of points here, and then we fit a line, a model to them. And it's quite easy. There is no points from outside this, this line. There are only points which belongs to that line. Case which is slightly more, more challenging is when there are points outside the line. So we call them outliers here. And there are points on the line, noisy points. And the goal here is to find the line, even though we have outliers, so points which should not be assigned to the line. And of course, there are more difficult cases when we have multiple instances and we do not know how many instances, for example. So if we have 3 lines or some planes, number of planes, number of homographies, number of rigid motions in some video sequence or something like that. And we aim to find all of them and assign the points, the data points which we have to them. So here you can see that color assigns the points to some line. Also, we can have the, I would think the most general case, the multi-class, multi-instance case, when we have, for example, such image, such edge map from a 2D image. And then we aim to find multiple instances originating from not necessarily the same class. So here the class is the circle and the line, and those are the instances of line, these are the instances of circles. Today, we will be talking about this robust single-class, single-instance fitting problem, but I just wanted to show you that there are more versions, more general cases for this problem. Some real examples to make it real. So we can have these images that are banknotes images from the previous slide, and this one, where we have circles and lines. We can have some fundamental matrix that is the rigid motion between two images, basically. Or we can have multiple homographies. Here you can see, I think, the first images. This four is the first images of some image pairs, and the points are assigned by color to the homography which they belong to. So this is a plane, or this blue one is a plane as well. Or we can have multiple motions in videos. That was supposed to be a video, but I lost the video file, so that is just the image now. But if that would be a video, you would see a bus and the car going with different speeds, and there's a background which has its own motion. And the aim here is to assign these yellow points to the background, these red points to the bus, and these green points to the car. So basically to find the rigid motions in the scene. Also, we can have different kinds of data. We can have LiDAR scans where we aim to assign to planes and cylinders. So you see a cylinder here. So that are just some examples for the fitting problem, for the robust fitting problem. And just to start from the beginning, what do we do if we have no outliers, just noisy points, noisy inliers of the sought model? So for example, we have these 2D points and we aim to find the line, and we do know that that there are no points outside, so there are no outliers. And it's then a quite easy problem. As soon as we know the equation of the line, then we, for each point, write these equations, put them in a big matrix, and do an SVD decomposition, which will be a least squares fitting. And that's an easy problem. We most probably can also solve that. But the problem happens when we have points which do not belong to that line. And in that case, you can see here that the least squares fit will not be the one which we are looking for. So here as well, and here. And the main problem is that even we can have thousands of points on the line, but if we have one very bad point outside here, for example, then the least squares fit, won't find the good model. Even if we have thousands of good points, it will be drifted away. This line will be drifted away even if we have one bad point. So least squares fitting doesn't work when we have outliers in the scene. And therefore, robust losses were discovered and were proposed. And the problem here is, the initial problem here is similar to the previous one. So if I go back, the problem was to find theta star, so the best model, which minimizes the loss function over the sum of loss functions over all points. That was the problem. It's the same here, so the problem is still the same, but we have different loss functions. We have robust losses. So the previous loss which we had is the least squares loss, a loss that didn't work. The reason is that where the residual was 0, so the point was on the line, the loss was very small. But as we get farther and farther, the loss will be quite big, and the point will have a huge effect on the fitting. In robust losses, for example, in ransack loss, we have something like this loss functions, robust losses, where if this is the residual in the horizontal axis and the vertical axis is the loss which it implies. And the thing which you can see here, that between -1 and 1, so you can imagine that as a threshold. So between some threshold, the loss is 0. So we like that situation. If a point is closer to the model, to the line, than some threshold, we have no loss, it's good. If the point, so the residual, is higher than the threshold, so we go out of this area, then we have some constant loss. So basically, we do not care if a point is very far or very bad or very, very bad. We just care if it's in or out. If it's in, then we have no loss. Otherwise, there is a constant one. Of course, there are different kinds of robust losses. For example, this truncated least squares loss. But the main idea behind them is the same. When we are closer than a threshold, then we have some. And when we are outside, then we overcome the problem which comes with. Okay, so some example how RENSEC works. So could you please please turn off the sound?
Yeah, Elena, could you please mute Oleg? Perhaps.
Thank you. Okay, so some example how RENSEC works. RENSEC is a method for robust model fitting. One of the most popular ones. I'm quite sure that most of you know how it works, but just to be sure, I will show on a basic example. So RENSEC, basically, this random sample consensus is an iteration. In each step, in the beginning of each step, it selects a minimal sample. So this means that it's for a line, a minimal sample is 2 points because 2 points are enough for estimating a 2D line. For a plane, it will be 3 points, and etc. So basically, it selects a sample which contains enough points for estimating the model which we are looking for. Then it fits the model, that is the line currently. Then it calculates the errors of all points to the line. And then it counts how many points are closer than the threshold. So if I go back, this is exactly what I've just shown here in the loss function. If it's close, then there is zero loss, otherwise there will be some loss. So basically it counts now how many points are closer. We have now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points. So the quality or the score of that line is 11. We repeat this procedure. It will be, I don't know, 10 maybe. And 10 is smaller than 11, so we just continue and do not do anything else. Now we have this one. This seems to be better. This seems to have more points, but let me count. 1, 3, 4, 5, 6, 7, something. So it will be, I don't know, 15 or 20, which is bigger, which is a bigger number than the previous best. Previous best had 11 points. It has, for example, 20. So we update the best model and then continue the sampling. And then we have some probabilistic guarantees of finding the best model which we can find. So this is the basic idea of RENSEC. And it's a quite simple algorithm. So what we did, we basically applied an iteration where at the beginning we selected a point, a sample, fitted a model, counted the inliers, and always stored the best model. And that was repeated. So it's an extremely simple algorithm. And the main question is if we can stop here. And of course, this question implies that probably we cannot. And because there are, even for such a simple algorithm, there are many things which can be improved and updated. So for example, we can talk about different cost functions. Maybe that's not the best to count the inliers. Maybe we can have some for example, MLSAC, some maximum likelihood loss function. Probably it will be better. Or also a question is how to set the outlier threshold. There are methods for that. I will be talking about later about these kind of methods, because it's not that easy. I mean, if we have different kinds of problems, we are working on images or LiDAR scans or whatever we have, this threshold is usually set manually, and it's not that easy to be set. Also, there could be different things. We can have degenerate data, degenerate models. We can have assumptions about what could happen in real world that usually are called chirality checks based on some visibility constraints. Or we can talk about how to improve the accuracy. So for example, we can have some local optimization procedure which improves the parameters wherever we find a new best one. Or we can talk about speed issues, how to speed up the procedure by, for example, designing a more clever sampler than just the random sampling, random selection of minimal samples, or with some preemption to stop the validation, the inlier counting, when we are sure that we cannot be better than the previous best. So there are many things which can be still improved. And the funny thing that if I went yesterday to Google Scholar just to check how many papers have will it give me for RANSAC, and it gave me 62,000, and out of them 1,200 contained in their title this word RANSAC. So basically, for such a simple algorithm, there are more than 1,000 papers containing just the name in the in their title. And this was I would say, the introduction of this robust estimation part. I'm planning to talk about two main topics. I would say these are the most recent topics, most recent things in published in the last 5 or 6 years. I'm sure I will have time for the first one, for the inlier, how to find the inlier outlier threshold. I'm not sure about the spatial coherence, but we will see. And yeah, so we will see for what we have time. So the usual case is the original setup is that we are looking for, we traditionally want to find the sort model parameters and the set of inliers. So the model, the line, and the points which belongs to the line. And the two problems of estimating the model from the inliers and getting the inliers from the model are usually considered equivalent, because whenever we have a set of inliers, it's easy to estimate the model with some standard estimation, least-square fitting or some numerical optimization. It doesn't matter. And as soon as we have the model and we have the inlier outlier threshold, we can select the inliers. So here there is a strict inlier outlier decision. So a point is either in or out. There is no in between. For that, I will be discussing the min-pran and a contrario RANSAC algorithms soon afterwards this. Or we could have another objective as well. So that was a traditional one when we consider the set of inliers and the model as an equivalent problem. Another objective which could be considered is to find the model parameters, but without really deciding what is in and what is out, and without requiring therefore an inlier outlier threshold. And for that, I will show it to you 3 different problems, 3 different methods. But first, a few words about why it's important to really propose methods which doesn't really get affected, which are not so sensitive to the inner outlier threshold. So for example, here you can see synthetic scenes where there are 2D lines and 2D points and the ground truth line. So that red line there is the ground truth line. And here you can see with these dotted blue lines, the ground truth threshold. And for finding these lines, for each scene, we would need a different threshold. We would need to know this threshold to exactly find the line which we are looking for. But this is, of course, synthetic scenes. So of course, it was generated in a way that it has different noise on the points. But it's the same. But it's the same things happens in real world. Please let me drink a sip of water. So the same thing happens when we have real world scenes. So on the top left 2 plots, you can see the results for homography. On the right 2 plots, you can see results for fundamental matrix fitting. And the thing which you can see here is that for one plot is one data set. The bars are different scenes in the data set. And for each scene, we selected manually and carefully the ground truth inliers, and then we fit a model to them. And that basically is, this number is the distance of the ground truth model, as average distance of the ground truth model, or sorry, not average, but RMSE the ground truth model to the ground truth inliers, which should be 0 in an ideal case, but it is not. And it's like even the ranges are different for the data sets. So for example, here it's 0.1, here it's I don't know, 0.8, goes up to 0.8. So there are quite big jumps between the scenes for the inliers and model, which should be ground truth. So the message from here is that there is no single threshold which suits all problems. And what could be the reason? So of course, there could be noise in the measured data. So we could have noise in the coordinates due to some detection failure, compression artifacts, resizing of the images, such things. But that's one thing. We can also have imperfect models. So for example, when we are fitting a homography or fundamental matrix, what happens if there's a small rolling shutter in the images? So for example, we have this helicopter and there's a small rolling shutter. Of course, no model will really fit well if which does not consider this rolling shutter. Or we could have radial distortion in the images. So for example, here, the lines are curves now. So if we do not consider when fitting the model that this radial distortion is there, then the model will be imperfect. Even if you find the ground truth model, which is of course almost impossible, we won't have 0 errors. And also, what happens if you fit a fundamental matrix and the scene is not completely rigid? Because for fundamental matrix, we assume that the scene is rigid. I mean, a part of the scene at least. But we can have different things as well. So we can have imperfect residual function. For example, when fitting a fundamental matrix, what do? We calculate the residual, the symmetric epipolar distance, which is basically the following. So we have 2 images. We have epipolar lines. These are the epipolar lines. And then we measure how far is the point from the corresponding epipolar line. So this distance and this distance, that is averaged, and that is the symmetric epipolar error. But the problem is that this point can move along the line without implying any residual, without having any problem, and we cannot penalize it. So basically, this residual function cannot penalize if the point moves along the epipolar line. It can penalize only if how far the point from the line. So that is some imperfect residual function. Or we can have different things. So for example, if the image size is different, so for example, we resize the image to its half, then the threshold should also be resized maybe to its half to get the same results, so who knows. Or even in one image, if we have close and far objects, different thresholds means, different things. For example, if we are fitting the bottle there, here, and if we let it, I don't know, it's 5 pixels or something like that. If we set the threshold to 5 pixels, this will be, I don't know, a few millimeters in real life. So it's still fine. But if we want to find the person, for example, that person, that 5 pixels threshold will be a bigger distance in the real world. And also, if we have some big building in the background or the Eiffel Tower 2 kilometers away, then even one or two pixels could mean meters in real life. So even for one image, the threshold is not that clear what it should be, and depends on the application and the scene, of course. And to solve this problem, there are several methods proposed. For example, there was the mean Prana algorithm, which I'm not sure what it abbreviates, maybe minimum probability random sample consensus, but I'm not entirely sure. It was proposed in 1995. So here the basic idea is that we assume that the outliers, so the points not belonging to the line, to the sought model, are uniformly distributed within the sensor range. So this means that inside the image, we have these points, these are uniformly distributed, and that is what we assume. And the idea is that we want to find the model, so this line, and the threshold, where the points closer than the threshold to the line are the least likely to have occurred randomly. So this is the basic idea. We want to find the line and the threshold where the points are not likely to have to be random, to be uniformly random. And instead of talking about these equations, I probably will show you just a video of how it works. So it proceeds as ransack first. So it selects a random sample, which is the two red points here. Then it fits a model that is the red line, and then it tries all the possible threshold values. I'm not sure why isn't it working. Let me go back and come back again. So it tries all the possible values. The current threshold is the blue line, and so far the best threshold is the green dashed line. And basically it tries to find the threshold where the points inside the threshold boundaries are the least likely to have occurred randomly. So there's some likelihood function which is calculated every time, this probability, and that is, and if we find a setup with a lower probability of being random, then we store that, and that's what is returned in the end. So this line and this threshold. And the second method, which is quite similar to this min-pran idea, is the a contrario ransack algorithm, which basically proceeds similarly. So it also assumes the outliers to have uniformly random distribution. The main difference between min-pran and a contrario ransack is that while in min-pran we calculated the probability of being random or not being random, here in a contrario ransack we calculate the expected number of false alarms, which you can imagine that this false alarm as a point which is uniformly distributed. So we minimize the expected number of points within the threshold boundary, which are uniformly distributed. But yeah, this is what I've just said. So same assumptions as min-pran, but different loss function minimize or different loss minimize. Yeah. And if I show you a video, yeah, so the procedure looks the same. First, it selects a minimal sample that are the red point dots here, then fits a line, so that is the red line there. And then it tries to find for the current line the best possible threshold by testing all possible thresholds. And it's not that hard. I mean, it's a discrete set. All possible thresholds are a discrete set, because as soon as we have this line in the beginning, then we can calculate the residual of all points from the line. So this point, this point, this point, this point, and this point, etc. And then these residuals are all sorted increasingly. And then we have all the possible thresholds. So no other threshold will lead to different set of inliers. Okay, and the next thing which I would like to talk about is not about finding the best threshold which suits our problem, but to really eliminate the threshold from the equation. Here the ransack algorithm doesn't even care about in theory, doesn't even care about the threshold, so it doesn't need it. The idea and the motivation of ransack is that the inlier and outlier threshold is hard to set, as I've shown it earlier. And also ransack results. So what happens in ransack? We always return the best model which we have found. And the motivation and idea behind ransack, this ransack, is that instead of just returning the best one, we should combine all the good hypotheses and use them to improve the results. But of course, it leads to many questions. For example, what does it mean to combine models? And they propose to average the models, but it leads to another question: what is an average model? And then they combined it in a way by weighted averaging. And also, it's an interesting question: what weights are robust for that kind of stuff? So staying at this averaging problem first, it's not that clear how to average models. For example, if you have a translation, then it's fine. I mean, 2 translations can be averaged. 2 rotations, yes, that works for SFM, doing rotation averaging, but as soon as we go for affine transformations, projective transformations, and such things, it's not that easy, not that straightforward to average models. And instead, the thing which they propose is to convert the models to points, basically. So for example, if we have a homography that is the top row here, we can somehow we got a homography, we estimated the homography, how to convert it to points. And they propose to select some anchor points. So for example, the corners of this image, and then transform them by the homography, by the model which we have. So this gets to here, this is transformed to here, that one to here, and that one to here. And it's enough to store the coordinates of these 4 transformed points to calculate back the original homography. And then we know how to average Euclidean coordinates, so we know how to average these points. The averaging procedure gets easier. So here, I think at the bottom row, you can see some radial distortion homography. And an example how it works. So here you can see an image pair, and you can see point correspondences. Some of them are inliers, good ones. For example, if I see it well, this bird's wing is found in both images, but for example, the frame here is assigned to another bird, and I'm quite sure that that bird is not the frame. And after doing many sampling and minimals, and so for each sample, minimal sample models as a model is estimated, we get something like this. That is basically the corners of the right image projected to the left image by the homography homographies which we estimate. So this is the way how we got these points. And if I zoom in, you can see that they are spread around the ground truth points. So that is the ground truth, that white one here, 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 here. So that is spread around. And they have so that their size depends on their weight currently in these images. If I zoom in, you can see that you can do many things now. If you have these points, we can estimate the mean, weighted mean, which is, I think, under the ground truth here, weighted geometric median, or geometric median that is here, some 2D median, or we can do ransack. Ransack is basically selecting the biggest points, so the point with the biggest weight. So that is basically the idea. We get back these, for example, the green point, if you have ransack, green, 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 and then we calculate back the homography, which these points imply. But it has a number of limitations. There are a number of questions, first of all. How to convert a model to a unique set of points? It's not that easy. I mean, for homography, fine, we converted the corners to the corners of some images. But what if we have fundamental matrices? What if we have some rigid motion in a video sequence? Or we have some more complex model, which is not that straightforward to be converted to points. And as I will show you in this next slide, even homography is not straightforward to be converted to unique set of points. Fine. And the next thing, which is also a question, how to convert points to a model. In most of the cases, yes, we do know how to estimate points from homography from points, or fundamental matrix from points. But what if we had affine correspondences? What if we had some line segments and such things? And then we do not necessarily know how to estimate from points the model. Also, in theory, it requires more than a single sample to be drawn to find the sort model parameters. What does it mean? So if I come back here, for ransack, I needed just one, this big one, and I was fine. But if I do mean or median or such things, I have to find it more times than before, so it will work. So finding the good model once is not enough. And also one limitation is that still in the end, we needed the inlier outlier threshold because the weights, so the sizes of these points were determined by the inlier outlier threshold. This comes from the inlier number. So in the end, the goal was not achieved, I would say, because the threshold is used. And also there is a fourth question about these conversion things. If it's robust, I mean, if it's robust to convert a homography to points, and the answer is not really. So for example, if we have this well-known Star Wars scene, and we project the homography from the corners to here and here, that's fine. But then that corner goes to infinity up here, and that one and one from this part would go to the same position. So we have we would have many points in the beginning at infinity, basically, and here. So that would mean that we have 3 points when doing the averaging. I mean, 3 different parts when doing the averaging, which are not enough to recover the homography. And also, what happens if the plane flips what we are currently estimating? So that corner goes there, that corner goes there, that one there, that one there. And when we try to estimate back the homography, it will be completely messed up because we do not know that the plane flipped, and therefore it will be degenerate, or we will not get back the original homography. And the next idea which I will be talking about is the max-sec approach. And interestingly, this max-sec approach was motivated by the previous one, by this ransack averaging. But instead of averaging over the model parameters, we average over the threshold values. So the idea here is to eliminate the threshold by marginalizing over it. So this means by eliminating the threshold by averaging out the threshold, trying all thresholds to estimate the model. And by this, we do not need a single threshold. And also, we do not make a strict inlier outlier decision. We do not really care about what the inliers and outliers. We want to find the model parameters. For that, we had some design choices. We considered the outliers to be uniformly distributed. That is a usual assumption done by the previous algorithms as well. And also, we considered that the inlier residuals have chi-square distribution. So what chi-square is, basically, if we have if we calculate the residual function as the sum of squared variables. So for example, that is the reprojection error or some residual functions which we often use. So we have squared variables which are assumed to have Gaussian distribution. If I sum them, then I will have chi-square distribution. So this is the reason why we chose that. But that is just the design choice. It can be changed to whatever we want. And the interesting thing for me that this chi-square should be used, by the way, also in ransack and other kind of robust estimation methods when doing two-view problems, because that is usually the case. That is usually the case when we assume variables or assume Gaussian distribution along the axis. I won't go deep into this equation. The only thing which is important that this is what we get just from putting together these data design choices, these distributions, the outlier and chi-square distributions. This is what we get. This is how we calculate the likelihood of model theta given some noise scale. Okay, so we have a function to calculate the likelihood of some model given some noise scale, and I will be using noise scale as a I don't know the word, so I will be referring to the noise scale as the threshold. So those are connected, one can be calculated from each other. Okay, so if I say noise level, then you can hear a threshold as well. And the new quality function which we proposed looks like this. So that is a quality function which was in ransack the inlier counting. We have this likelihood now, and we have this Q now. And the thing which happens that we put the likelihood of a model given some sigma in an integral to integral out the sigma value and then we average over sigma max, where sigma max is some loose upper bound for the noise scale, which can be selected from a much wider range than the original threshold value. And this is how you can imagine this as a progressively widening threshold, basically. So we try all the possible threshold values. We calculate some likelihood, and we increase likelihood, and that is averaged. And that is averaged out, basically. But we now have two problems. The first one is that we do not know about the inliers. We do not know which points are inliers and which are outliers. And therefore, we cannot do the final thing, which is always done when applying RESEC, which is to apply a least squares fitting on all the inliers which we found. Also, because we do not know the inliers, we do not know their numbers, and therefore we can't apply the standard termination criterion. We do not basically know when to stop with the sampling and the iteration of RESEC. To solve these problems, first we proposed the method for this to solve this missing least squares fitting in the end, and the idea was to estimate the inlier probability. So given some model, we have some model which maximizes this quality shown here, and then we want to do some least squares fitting on all the inliers. And the thing which we did is to we estimated the likelihood of model of point X given some theta. So that is the inlier probability of a point. Yeah, so this is the inlier probability of a point. This can be easy. This is easy to be calculated since we know the theta, and that is simply just the likelihoods what we chose. And in the end, when we had the likelihoods of the points, they are put in a weighted least squares fitting, and that is how we estimated in the end the inlier probabilities. I mean the final model. And an interesting thing here was that we were able to replace the integral by the summation, because that became a piecewise constant integral. Because when you increase the threshold, there are just particular thresholds where a new point comes in. Otherwise, it's constant. I mean, the number of points constant. Another problem is as I've told you before, is that the termination criterion of RESEC is not applicable, which is as follows. So we have some function k which determines how many iterations should we do. And we calculated by setting some confidence, which usually is, I don't know, 0.95 or 0.99. That's our usual values. And it depends on the inlier ratio, that is the inlier ratio, and the sample size. So which is 2 for a line, 2D line fitting, where 2 points are enough for estimating the line, or for a plane M is 3. So that's other things from which this termination criterion depends, on which the termination criterion depends. And the idea was the same as before. Let's marginalize over this function. So we get this, which do not depend on this noise scale. And basically we calculate the average out the iteration numbers in this range of noise scales. And the algorithm is as follows. So here is what I've just tried to tell to you. You can see here an initial model where we would like to now determine the quality of the model. And the thing which happens is that we have an progressively increasing threshold. For each threshold, we select the inliers, so the points closer than the threshold to the model. And then to the points we fit a temporary model, that is the dashed red line, and that is then used to estimate the quality of the and also the inlier probability of the points. The good things with MaxSec is that on the tests which we perform, by the way, I won't show you any tests today. I don't think that's so important. If you want to see tests, you can find them in the papers. But the good things which we found is that it was quite accurate with quite small failure ratio compared to the competitor algorithms, and also that sigma max, as I've just said, it was much easier to be set than the original inline outlier threshold. Being much easier, I mean under being much easier, is that it can be selected from a, I would say, an order of magnitude wider range than the original sigma. But the problem is that for every calculation, if I come here, we needed to do a least squares fitting on the inliers, which can be quite time consuming if we have to do it many times. So MAXAC can be slow on some problems. The idea was to solve also the speed things and also to improve the algorithm is the following. So we assume the same things about the, we assume nothing about the outliers. Since in most of the cases, I would not say it's true that the outliers are uniformly distributed. So for example, if you imagine, just for the sake of showing it, I go back to the beginning. I close it. To the very beginning, just to show. So here, I came here. So, okay, the outliers which do not belong to any points seem to be uniformly distributed, they are. But the problem is that when we aim to find this almost horizontal line, then all the other points which belong to this line, for example, this line, will act as outliers. And those points won't have a uniform distribution. They have their own distributions depending on the line from what they originate. So therefore, the outliers distribution will be a mixture of uniform and different distributions. So therefore, we do not assume the outliers to be uniformly distributed. We just simply do not assume anything about that. And let me quickly find where I was. Okay, so I come back here. And yeah, so this, there is no assumptions about the outliers, and we assume the same things about the inlier residues. So they have chi-square distribution. Of course, the algorithm is capable of assuming anything else. It's just the design choice we made. And the idea is to replace this expensive, least progressively widening threshold by some iterative derivative least squares, where the model in the I+1 iteration is calculated as the weighted average of the by weighted least squares fitting, where the weights come from this marginalization procedure, where this is the likelihood and these are some M estimator to estimate the weights. So the marginalization is in estimating the weights, and then using those weights, the model is updated in every iteration. And of course, we can now define a new quality function, and that will be the sum of losses, basically, but I don't think it's that important to go into deep into these equations. But the most important things here from this slide is that in contrast to MAXAC, we are able to calculate this precisely and also efficiently by using a lookup table. Yeah, funny thing that on the current GitHub implementation, that lookup table is I don't know, a few megabytes big text file containing all the values which are needed, but that will be solved soon. So the contributions of this part about setting the threshold is that the main thing is that the threshold is not that easy to be set problem by problem, especially if we have some large scale problems with thousands of image pairs and thousands of scenes, which may originate from different sensors and different times and etc. Setting threshold is not easy. And so far there was 3 types of attempts to solve this problem. The first one is the ransack solution, is that we do not need any threshold. We just use minimal sample models and do averaging or do whatever with them to get some good model. That was the first. And then there's something in between which says that we need some threshold, but we try to find it adaptively, depending on the data what we currently have. And also we have the other side, which says that we can marginalize over a range of thresholds. So we can basically use all possible thresholds, all of them in the range, to get some good results. And I'm quite sure there could be another part, but I'm quite sure I don't have time for that. It's I haven't measured the time, but I think it's soon over. So if you have any questions, then I'm open for questions and answering to them. Now I go back to the presentation here. Okay, so I'm here.
Okay, colleagues, please go ahead with your questions. You may just unmute and ask them or put in chat. I think there is one question from chat, Daniel. So from
I just opened the chat.
Okay.
These images are based on RGB or depth camera source. Which images?
Michal, probably you may unmute and specify your question, please. Out question.
From beginning here. With vegan presentation with points here. Yes, here. Where do you see that RGB? And that one is the only one with depth, but that is a LiDAR scan. Everything else is just images. Good. I answered one question.
Yep. Colleagues, please, any more questions? Okay, Daniel, then let me ask one question. So on slides 39 and 40, you showed this corresponding finding by Ransack on the picture, on the...
I do not see the page number, so I don't know.
Oh, really? So that's 17, 19, 20.
Oh, okay, I see now. So which number did you say?
39, 40. So when you found the correspondence. And there are several points corresponding to Ransack. So, and when you tell that those points correspond to Ransack runs, does it mean that you find a kind of 4-point, and then find a number of inliers? Based on that, make a judgment and just provide a reprojection based on that 4 to 4, or you make some adjustment based on all the inliers, like.
So in theory, in this method, there is no selection of inliers. So in theory, the thing which happens is that you select 4 points, get the homography, and then convert these points immediately, so you get 1 point from here, for example. But the method didn't work. So method doesn't work without really selecting inliers. So the same thing is done. So 4 points and then 1 point here. But the size of the point depends on the size of the on the number of inliers, basically.
But no kind of procedure of mean squaring.
No, nothing like that. Nothing.
Yeah, clear. So and okay, yeah, got it. And probably one more question from my side, or probably anyone else want to step in?
I think let's ask, and then everybody else can ask.
Yeah, colleagues, I think that's really a practical speech, and there are a lot of stuff to get out of this. So,
yeah, and that is the interesting thing that one. So I was talking about just this how to set the threshold if I go back. But even if it seems to be such a simple algorithm, but I was just talking about this threshold selection, and there are a number of different things which we could talk about, and which can be still improved. So I think there are a number of open problems, even with this very simple algorithm of iterating and trying.
Yep. may I again ask one more question from my side? Do you have any recommendations, Daniel, on how to deal with multiple class ransack? Meaning there are a lot of strategies here, like truncating or making several distribution at once, or etc., which increases in complexity. Do you have anything from practice how it would work better? So probably applied to some specific problem that also.
Yeah. For that, I would refer to. So we had a ransack tutorial at CVPR, and Dimitro made a lot of tests and experiments to see what really works well in practice. We compared a lot of methods, and the thing is that you get good results. First, it's very important to have a good implementation of whatever you use. And usually it's problem dependent what is helpful. So for example, for fundamental matrix fitting, it was quite important to have degeneracy, so degeneracy testing. Local optimization is almost always needed, but then you can. So yeah, I would say it's problem dependent what to use. But if you check Dimitro's talk in the tutorial, there for homography, fundamental assertion matrix, there is a quite a good guideline, I think, what to use and what leads to the best results. But yeah. So
I believe that you actually answered a little bit different question. Maybe Victor asked about multi-model ransacks, like when you have several planes and so on. No.
Yeah, exactly. So when
I misunderstood you. I'm really sorry. I have that talk in the end of this.
So I mean, what is the best practice you would suggest from practical standpoint? So I understand there are a lot of strategies, and you read months about strategies, but what worked for you?
Yeah, it's a hard problem. I mean, it's far from being, even this robust estimation, as I would think, far from being solved. But this multi-instance, multi-model fitting is really far from being solved. And I think some practical thing, the thing which I first tried when doing any multimodal fitting, and which worked quite well, is the simple sequential ransack. When you do what? You have the data, you apply the model fitting ransack, find this line, remove the points of this line, and then apply again. That will work on any amount of points. That will work to find the dominant models. It won't find any sophisticated small models which may be spatially coherent and therefore seems to be a good model. But it will be good if you want to implement something fast and you want to implement it fast. So yeah, but of course there are a number of things to apply. So for example, we had this progressive X algorithm. I also have a video which is basically a mixture of global optimization and this ransack. When I go here, when then in each iteration, like in ransack, we try to find a new model, and then we maintain a compound model consisting of all models, and then there's some global optimization. But you can try this code. It's online if you want. I can help if you want it. But yeah, it's for some practical thing. I think if you want to start multimodal fitting, sequential ransack is the best algorithm to start with. It will work. It will have nice results, and you will find the dominant models in the seed.
Yeah, sometimes it just cuts some points for the second model when you cut the first one in Centra, especially.
Yeah. So it's a greedy algorithm. It won't be the best, but the interesting thing that some of the sophisticated algorithms still won't work better, I would say. So many of them are quite slow and can be applied only to just a few hundred points, otherwise they die because of their complexity. And some of them are just not that stable or require problem by problem threshold setting. So for example, the interesting thing for me that papers from the last, I don't know, from the last 5 years or something like that, from CVPR and such places on multimodal fitting, many of them has scene by scene threshold setting. So not data set by data set, scene by scene. So, and that results are reported. And that is nonsense, I would say.
Yeah. Okay. Thanks for that. At least that answer means that straightforward doing what you have done is not that bad.
Yeah.
That's a good good hint here. Thanks. And I believe there are 2 more questions in chat.
No, let me go there. Let me read. Okay, Dimitro posted thank you, Dimitro. What was Nikolai's question? What will be the effect if we are watching one object in an image where there are multiple identical objects? I think that's the question mostly of the feature matching procedure. I mean, when you found the good correspondences, then you will find, so the robust estimation will find the good model. Of course, in that case, when you have multiple identical objects, it's not an easy problem to find the good correspondences. As soon as you have them, the robust estimation will work.
I believe I can quickly answer. So if you have such problem, then just increase scale of your template or feature matching and so on. So, and include the context. And context usually easily disambiguate like repeated patterns or objects. Like if you have 5 people, then one would be to the left, and near the left there would be some background and so on, and it will solve your problem, hopefully. Sorry for interrupting.
Thank you. So question of Vitaly, if there is any good baseline for robust linear. I think there are a number of, most probably I will for my first attempt would be to use RANSEC or some robust things. But I think for linear problems, there are more sophisticated methods, which I'm not familiar with. So I'm maybe not the best to answer for this good baseline for robust linear regression. Yeah, but there are many good, for example, iterative related least squares approaches, which are quite good in these kind of things. And also, so default thresholds, I would say it's problem by problem. It depends on the problem. For homographies, a few points, 2 or 3 pixels or 2 pixels, 1 pixel, I don't know, sure, will work fine if fine is enough. Also, it depends on the problem.
Hi, Daniel. Thank you for presentation.
Thank you. Yeah, you can ask you.
Yeah, I want to ask one quick question. So you mentioned that this multimodal can be used for rigid, non-rigid motion separation. Did you try anything in practice on some data sets, and did something work for you?
You mean rigid motion or non-rigid motion? I did not hear well.
Different motion from the same scene.
Yeah. So first of all, if you get a scene and do multiple fundamental matrix fitting, that is a multi-rigid motion fitting, because in that case, each fundamental matrix will be a rigid motion. But if I come here, I don't have video for that. But so yeah, all these algorithms can be applied. I come here back to the beginning. So all these algorithms which can do model fitting can easily do multi-rigid motion fitting. Of course, if you have a video and you want to find multiple rigid motions in the video, then you have to create point trajectories to find. So that will be an affine space, and you fit an affine space basically in the trajectories. So most of these algorithms which work well for robust fitting or multiple model fitting will work well for multi-rigid motion fitting. Yeah, for most of these motor papers which we made for multi-motion fitting, we all had tests for multi-rigid motion fitting.
Okay, thank you.
But if you ping me afterwards, I can send you whatever helps or what you want.
Yeah, thanks.
Okay, any more questions, colleagues? Yeah, then let's say thank you to Daniel. Daniel, thank you for your talk.
Thank you.
Practical, and I believe there are links that everyone may follow. So that's it for this official part of this day 2, but we still will open rooms within the same configuration that you put. So you still have a few, I mean, maybe less than a minute to change your number near your name, or actually select one, because there will be rooms opened during next, I think, 20 minutes. Definitely that is optional. So that is a kind of, yeah, a kind of after party without after party, right? But for open chat. And I'd like to thank everyone who joined today, and especially thank you, Adrian and Daniel, for your talks. There will be a video afterwards, and also here is a link from Dmitry on CVPR tutorial on related to the last talk. Yes, thank you all, colleagues, and we will be happy to see you on next Thursday, on the third day, which is dedicated to business and investment in computer vision and machine learning. So it's free chat time now, and have a great evening today. Yep. Bye.